Of all the things we do with indices, perhaps the most important at this level is being able to work with an unknown indice, okay, or an unknown index, because indice is plural. If you have something like, for example, 2 to the power of 2x is equal to 4, or it's something simple as that, just write that down. 2 to the power of 2x is equal to 4. Now, to start off on something as simple as this, when you have an unknown index, the key thing to remember, first off, is that every base must be written to the same term. So here on the left hand side you've got base 2, here on the right hand side you've got base 4. Different bases, you just don't work with them when we're dealing with indices. You keep the base the same and then you work with the indices. Okay, so what I know I can do here is I can turn 4 from 4 into 2 squared without changing its value. All right, and now I notice that base 2 is on the left hand side, base 2 is on the right hand side, so because both of the bases are the same, I end up just equating the indices, and I get x equals 1. And that is as easy as they are, providing that we can understand that in order to get this to work and in order to be able to solve an unknown index, the bases of all terms must be set to the same value, okay? And usually, a bit of a hint, usually the base that we work with is the lowest of all given bases. So let's just take a look at some examples. It's going to make it easier for you to actually do some of these things. The laws of indices are engaged most when we try to solve an unknown index or power. The equation must first be written in terms of the lowest base. Now, that's the first thing I would do when I'm doing a question like this. I'd look at all the bases I have, I would see which one is the lowest, and then I'd ask myself, how do I change the others that are of a higher base to the lower base? And usually, say for example, if the lowest base is 2, the other bases might be something like 8 or 16 or 32 or 64, something that can be written as the lowest base to some power, okay? Then the appropriate index laws are applied. Now, I spent a while the last class going through what all the laws of indices are. You do need to know them. They are in your tables and they are on page 21. So when you're doing indices, my advice to you would be that you have page 21 open in front of you and you keep your eyes on the left-hand column. That's where the index laws are printed. So for example, solve 4 to the power of x is equal to 8 over root 2. Now, rule 1, when you're dealing with solving an unknown index, rule number 1, what's the lowest base? The lowest base is 2. So therefore, every other number must be written in the form of 2 to the power of something. Okay, so I'm going to rewrite this straight away. Not 4, but 2 squared. Not 8, but 2 cubed. See that? So therefore, what I now have is 2 to the power of 2 to the power of x. So in other words, I'm going to write that for as 2 to the power of 2 to the power of x. This one here, 2 to the power of 3, root 2. Now please don't forget, that's a square root. Square roots are related to indices of halves. So the square root is the same as 2 to the power of a half. So let's rewrite this thing in terms of base 2. 2 to the power of 2, that's 4 to the power of x, equals 2 cubed, that's the original 8, over 2 to the half. And now, there's only one more rule. Apply the appropriate index law. The only index law that I can apply on the right-hand side here is the division law, which says that if you're dividing the same base with different powers, you keep the base and you subtract the powers. So 3 minus a half, 2.5. On the left-hand side, the only index law I can apply is the law that tells me what to do when two indices are separated by brackets. Whenever brackets separate two numbers, it's automatic multiplication. So that becomes 2 to the power of 2x. All right. Now, look at the left-hand side, look at the right-hand side. The base on the left is the same as the base on the right. So therefore, I can cancel the base on both sides. I get 2x is equal to 2.5, which means that x must be equal to 1.25. And that's it. So there's only 2 rules for what we're about to do in this section. Very small section this morning. Plenty of questions to do afterwards, so I'm not going to labour you for too long with talk. I'm going to do a few examples and let you off to do some yourselves. Rule 1. Find the lowest base. Write every other term in that lowest base. Rule number 2. when you have every term written to the same base, which is normally the lowest base, apply the appropriate index laws on the left-hand side and the right-hand side. Get both sides, if you can, down to one base. And then if the bases match left and right, you cancel them and you simply work with the indices. Okay. So here's one from page 180, question 3, part 2 and part 4. Solve the following equation. 3 to the power of x minus 5 is equal to 27. Now, look at the left-hand side, base 3, right-hand side, base 27. What's the lowest base in this question? 3. Can 27 be written as 3 to the power of something? Yes, 3 to the power of 3 is 27. So I'm not going to use 27, I'm going to use 3 to the power of 3. So I end up getting 3 x minus 5 on the left-hand side, 3 to the power of 3 on the right-hand side, and as long as the bases are the same left and right, you can cancel them, and you can end up with an algebraic equation that says x minus 5 equals 3, therefore x must be 8. Okay, that's it. Next one. Solve the following equation. 7 to the power of 2x equals 1 over 49. Again, rule 1. What's the lowest base? 7. Can every other term be written to the base 7? And the answer is yes. Now look, there's two ways to do this. Let me do the first way. 7 to the 2x on the left hand side stays as it is. Remember what the rule told you, that 1 was equal to. If you go down the rules of your indices, any base to the power of 0 is 1. So you could write 1 as 7 to the power of 0. You can also write 49 as 7 to the power of 2. So now I end up with 7 to the power of 2x equals 7 to the power of 0, that's 1, over 7 to the power of 2, which is 49. Now apply the appropriate indice rules, or index rules. On the left hand side, nothing to do, 7 to the 2x. But on the right hand side, you're dividing the same base, so you keep the base and you subtract the powers. 0 minus 2 is minus 2. Left hand side, right hand side, do the bases match? Yes. Cancel them. What do I end up with? 2x equals minus 2, x equals minus 1. Okay, let's increase the complexity a little bit. Question 4, part 6, and question 6, part 2. Solve this equation. 8 to the power of 4 over 3 is equal to 2 to the power of 5x minus 2 over root 2. Same rules again. Who's the lowest base? The answer is 2. So therefore, everything must be written in terms of base 2. Now let's take the left-hand side first of all. The left-hand side, instead of using 8, I'm going to use 2 to the power of 3 raised to the power of 4 over 3 equals, top line, keep it as it is, 5x minus 2. Bottom, don't use a symbol. The square root is the same as 2 to the power of a half. Index rules to be used on the left-hand side. There's a bracket separating two numbers. What happens when I multiply 4 over 3 by 3? It becomes 4. The 3's will cancel. So you get 2 to the power of 4 on the left-hand side. On the right-hand side, what's the rule? If you're dividing the same base, keep the base, subtract the powers. So 5x minus 2 minus a half. So 2 to the power of 4 is equal to 2 to the 5x minus 2 minus a half, minus 2.5. Okay, base is the same left and right? Yes, cancel them. 4 is equal to 5x minus 2.5. Now, use your ordinary powers of algebra here. You've got 4, bring them, add 2.5 to both sides, I should say. So 6.5 is equal to 5x, which means that x will be equal to 6.5 divided by 5. Let's do that quickly. 6.5 divided by 5 comes out as 1.3. And there's your answer. Okay, so again, I'm just the same procedure for every one of these. What's the lowest base? Turn every term into the lowest base. Apply the rules left and right. Get both sides down to the same base. Cancel a base. Work with the powers. Hence, that's the reason why this section of the chapter is called Indices, because you're only working with the powers. Okay. Second one. This is question 6, part 2 on page 180. 25 to the x equals root 125 over the cubed root of 5 to the power of 12. Now, rule 1. Who's the lowest power? Or lowest base, I should say. Lowest base is 5. So therefore, 25 must be written as 5 to the power of something. So we're not going to use 25. We're going to use 5 squared to the power of x on the left-hand side. Equals, keep your brackets in place, the square root of 125. Now just be careful for a minute. Let me just take that over here. The square root of 125. Deal with the symbol first. Okay, that's 125 to the power of a half, because that's what a square root represents in terms of an index. Okay, square root belongs to the half family. So therefore 125, that's the square root of 125. And then the square root of 125, if you leave it as that, change the 125 into base 5. So what's 125 to base 5? Well, 5 5s are 25, times 5 is 125. So that becomes 5 cubed to the half. See? That's all I'm doing. What does the rule say about numbers being separated by brackets? Multiply them. What are 3 halves? 3 halves are 3 over 2. 3 halves, 3 times a half is 3 over 2. So there's the top part. Okay, so that becomes 5 to the 3 over 2. Now 12 is still out there. Over. So let's take this one out here. The cubed root of 5. What fractional index is the cubed root related to? Think. The cubed root is related to the fractional index a third. Okay, so that becomes 5 to the power of a third. Nothing more I can do there. Bring that down here. Okay, so on the left hand side, the only rule I can apply is the rule that tells me what to do when 2 indices are separated by brackets. Multiply them. So I get 5 to the power of 2x equals. In here, now I don't mind what way you do this. Okay, you could say to yourself, oh look, I'm dividing the same base, let's subtract the powers. Well, let's do that. Let's see what happens. We're going to keep the 5. We're going to subtract 3 over 2 on the top minus a third on the bottom. And that's going to give me 7 over 6, which is still raised to the power of 12. So finally, 5 to the 2x equals, now again, brackets are separating the 7 over 6 and the 12. 6 goes into 6 once, 6 goes into 6 twice, 6 into 12 twice, 2 7s, 14. And straight away, I have the left and the right down to one base. The bases match, lose them. What do you get? You get 2x equals 14. So therefore, x equals 7. They're getting a little bit more complex, but there's nothing in these questions that's not on page 21 of your tables. And by right, page 21 of your tables should really be up here. Through practice, hopefully that's where they will go. Okay, so just the final part of these now. If I take ones that involve index equations. So here we've got a situation where we've got 3 to the power of 2x plus 1 minus 28 times 3 to the power of x plus 9 is equal to 0. Go back and think for a moment. What did we do in the previous questions? We took the lowest base that was needed in all terms. Okay, so in this case here, what do I notice? The base there is 3. The base there is 3. Okay, so we're on to something. Now, think very carefully about what that means. That means that if the powers are being added, the bases were originally being multiplied. It's rule number 1 on page 21. And here's what rule number 1 says. AP multiplied by AQ gives AP plus Q. In other words, if you multiply the same base with different powers, you keep the base and add the powers. But the backwards rule is just as valid. In other words, if you've got a base with a sum, then originally both of those indices belong to the same base. So what I can do here is I can write this as 3 to the power of 2x multiplied by 3 to the power of 1 minus 28 by 3 to the x plus 9 equals 0. And I hope you see why I did that. I did that because now inside in both my first term and second term, 3 to the x is present. Okay, but let's just see if I can further refine this down to isolate 3 to the power of x. Can I get 3 to the power of x out here? Let's see what I can do. 3 to the x times 2. Now, multiplication is commutative, okay? So 3 to the 2x and 3 to the x2. They're exactly the same. Because this 2 and x are being multiplied, the order in which they're multiplied doesn't matter. So therefore I'm going to write it this way. Multiplied by 3 to the 1 minus 28 by 3 to the x plus 9 equals 0. Now what do I notice? Now I have isolated the smallest base with the smallest power in the first term and the second term. And the reason why I do that is because this is quite a difficult quadratic to solve. So what I'm going to do is I'm going to allow y to stand in for 3 to the x. So in other words, everywhere there is a 3 to the x, I'm simply going to call it y. Watch what happens. You get y squared times 3 minus 28y plus 9. It falls out into a quadratic equation. You've spent your life doing quadratic equations, so this one is a very simple thing to solve. 3y squared minus 28y plus 9 is equal to 0. So therefore you can open your two brackets, or you can use your minus b formula. I don't mind which one. They'll both give you the same answer. 3y squared is 3y by y. Factors of 9 that give 28 are going to be, well, 3 3s are 9. Let's see if we can work this out. 9 3s are 27, so 9 1s. And I want minus 28, so both of those are negative. Now check the two outside terms. 3y by y, 3y squared. Check the two last terms, outside terms. Minus 1 times minus 9 plus 9. Now, get the outside and inside together. 3y times minus 9 is minus 27. Minus 1 times y is minus 1. Minus 27 minus 1 is minus 28. Which means that 3y minus 1 equals 0, giving me 3y equals 1, y equals a third. And the second one is y minus 9 equals 0, y equals 9. So there's your two answers. But they are not the answers to the question that was asked. The question that was asked was solve the equation 3, 2 to the x. So in other words, you've got to find out the value of x. Now, once I know what y is equal to, what did I allow to stand in for y? I allowed 3x, or I should say, what did I allow y to stand in for? I allowed y to stand in for 3x. So what am I going to do? Case number 1, change your y back to a third. 1 over 3 equals 3 to the x. And then we fall back on the rules we had in the previous section. 1 over 3. A fraction can be written as a negative power. Remember I told you that? Negative powers always involve division. So that, thanks to your tables, is 3 to the minus 1 equals 3 to the x. Same bases on equal side. Cancel the base. First answer, x equals minus 1. Okay. Take the second case, where y is equal to 9, and put 9 in for y. 9 equals 3 to the x. And again, what's the lowest power, or lowest base? The lowest base on both sides is 3. So turn that into 3 squared. That's equal to 3 to the x. Cancel the bases, and you get 2 equals x. And they are the two answers that do the job for x. So there's 3 steps to this, okay? The first part, and probably the hardest part, is to identify the term that you wish to isolate. And normally, in these type of questions here, the term that you wish to isolate is the term of x that is in the middle of your quadratic. So in other words, 3x. I want to get 3 to the power of x out of this. So the first thing I do is I remember, if the base has a sum as a power, then both of those numbers were originally indices of 3. So it becomes 3 to the power of 2x times 3 to the power of 1. Okay? 3 to the power of 2x. What does 2x mean? 2x means 2 multiplied by x. So it doesn't matter whether it's 2 multiplied by x or x multiplied by 2. Multiplication is commutative. So you can write this the other way around. So instead of writing 3 to the 2x, I write 3 to the x2. And I put brackets in between the x and the 2 to isolate the 3x to match this term that's in here. So once I have 3x, 3 to the power of x in the first term, and 3 to the power of x in the second term, I allow substitution to take over. I stick in y for the 3x, I get my quadratic, I solve my quadratic, get both of my values there in terms of y. Then remember that y was only allowed to stand in for something. So y was allowed to stand in for 3x. So I now go and say, well, hold on a sec. If y was equal to a third, what's the first case? It's a third is equal to 3 to the x. 1 over 3. A fraction can always be written as a negative index. It's 3 to the minus 1. 3 to the minus 1 equals 3 to the x. What does that mean? X equals minus 1. If the bases are the same on both sides, eliminate them and just work with the powers. And finally then, the second value of y is 9. So put it in here. 9 equals 3 to the x. Turn 9 into 3 squared to match the base on the right hand side. Cancel the bases. 2 equals x. Okay. So let's try one of these. Solve for x in 2 to the 2x minus 6 2 to the x plus 8 is equal to 0. Now remember what I told you? The key term in all of this is the one that's in the middle. The one that has the single x. So that is my focus of attention. And I need to build that in here. And I did tell you that 2 to the power of 2x is exactly the same as 2 to the power of x2. Don't be afraid to swap these round. And straight away, I can put a bracket around the case term that I'm looking for, which is 2 to the x. Minus 6 to the 2x plus 8 is equal to 0. So now I've got 2 to the power of x in the middle term. I've got 2 to the power of x isolated in the first term. Let y equal 2 to the x. So you're going to rewrite this time, this equation here, but instead of using 2 to the x, I'm going to allow y to take its place. Y squared minus 6y plus 8 is equal to 0. Open your brackets. Y squared is y by y. Factors of 8 that add to 6 are 4 and 2. And I want them to add to minus 6. So minus 4 minus 2. So y is equal to 4 and y is equal to 2. However, it's not y we're looking for. We're looking for x, solve for x. So now what do we have up here? Case number 1. Y is equal to 4. So let's put that in there. 4 equals 2 to the x. Check this equation. The lowest base is 2. Change the 4 to base 2. 2 squared equals 2 to the x. The base is the same on both sides. Cancel them. You end up with 2 equals x. There's your first answer. And secondly, put the second case value in here. Y is now 2. So 2 equals 2 to the x. Now again, 2 is better known as 2 to the 1. If there's a number on its own, it always automatically carries the power 1. We just never bother to write it down, but it carries it. Equals 2 to the x. So what does that mean? Cancel the bases, and that gives you 1 is equal to x. And that's that one. Okay, now I'm going to clear this to make space for question 9 part 4. So you can rewind that video if you need to go back over it again. I'm just going to clear it now to make space for the second question. Okay, so now what do I have? Solve for x in 3 to the x minus 3 to the 1 minus x plus 2 is equal to 0. Now, in a situation like this, when we have a negative power, please remember that the reason why we are subtracting powers is because originally the bases were being divided. Rule number 2 in your tables. A to the p over a to the q equals a to the p minus q. So if you're subtracting indices, the reason why the indices are being subtracted is because the bases with those indices were originally being divided. So let's do that. 3 to the x minus, now 3 to the 1 is on top and 3 to the x is on the bottom, plus 2 is equal to 0. And straight away, you've got your 3 to the power of x in both terms. Okay, so just keep an eye on those rules all the time. When you've got powers that are being subtracted, the bases were being divided. When you've got powers that are being added, the bases were being multiplied. Rule 1 and Rule 2 on page 22 of your index rules. Now, my golden rule, when I read this equation here, don't work with fractions. Okay, so don't work with fractions. So I want to clear the fraction. Now, to clear the fraction, I have to multiply every term by 3 to the x. To clear that bottom denominator here from this fraction, I've got to multiply across by 3 to the x. So let me just use a different color here and show you. So I'm going to multiply this by 3 to the x. I'm going to multiply this by 3 to the x. I'm going to multiply this by 3 to the x. Okay, so let's see what happens. 3 to the x by 3 to the x. What happens? The rules take over. When you're multiplying the same base, you keep the base and you add the powers. See that? Next, minus 3 to the x cancels with 3 to the x and leaves you simply with 3 to the power of 1. Plus 2 times 3 to the x. Now, what we notice is the term I wish to isolate. The term I want to isolate is 3 to the x. Remember what I told you about 3 to the 2x? Rewrite it as 3 to the x2. And put brackets around 3 to the x. Minus 3 plus 2 times 3 to the x is equal to 0. So there's where I've made the biggest change. Okay, and now what I'm going to do is I'm going to let y take over. So let y stand in for 3 to the x. What do I get? I get down here y squared minus 3 plus 2y. In other words, y squared plus 2y minus 3 is equal to 0. There's your quadratic. Open your brackets. Y squared is y by y. 3 factors of 3 with a difference of 2 is 3 and 1. And I want a difference of plus 2, so it's plus 3 minus 1. So y is equal to minus 3. There's the first case. And y is equal to 1. There's the second case. Now, what did I tell you y was standing in for? Y was standing in for 3 to the x. So we now have to go back and undo that. So in the first case, y is equal to minus 3. So minus 3 equals 3 to the x. Okay. Now you'll notice here that the bases are not the same. There's no power that can give you a negative number. Think about it. There is no power whatsoever that can give you a negative number. Negative powers give fractions. Positive powers give multiples. But there's no power that can give you a negative number. So therefore we can reject that straight away. Okay. The second case is where 1 is equal to 3 to the x. Now just be very careful. I need to get the base 3 on both sides. So there's a rule in your tables, rule number 4, that says any value to the power of 0 is 1. So I can rewrite 1 as 3 to the 0 equals 3 to the x, and you can see straight away when you cancel the 3's that x is equal to 0. And that's the question. Okay, now you can go over that as often as you want to. I'm going to stop at that. I'm going to leave you with some to do yourselves. They all work on the same premise as what you've just seen, the questions that we've done. Feel free, go over them as often as you need. Tackle the questions on page 180, page 181, the ones that are here, and we will go through these questions along with the introduction to indices in our next live class.